about thermal management of lithium-ion cells and battery packs. So far, we have been sort of looking at the science of lithium-ion batteries. In this lecture, I will talk a little more about the engineering, thermal engineering of batteries. In other words, the question is, how do we cool a cell or a battery pack? That's the main question. A secondary question also is, how do we heat a cell or a battery pack? About 90% of the times we are worried about the cell getting too hot and then a need to cool it down. But sometimes there is also a need to heat up the cell. If you have an electric car and you need to operate at very cold temperatures, then to start your car you have to first heat up your battery pack. So we are worried about both heating and cooling of the battery pack, and that's what I will talk about today. Okay. The need for cooling something is not new. If you look at the evolution of thermal engineering, we have over the past several decades worried about cooling of a variety of other engineering systems as well. Okay, the one that I am most familiar with is the cooling of computer chips. Dr. Chandar, who gave a very nice lecture on this, has a career built on the cooling of computer chips. So what happens in computer chips is that the little chip inside the cell phone or the computer generates a lot of heat, and that heat has to be removed in order for it to work, right? And so in the past 30-40 years, there's been a lot of research on the cooling of computer chips, and it turns out that a lot of lessons that we have learned from there can be used for the cooling of lithium-ion cells as well. Okay, so I want to talk briefly about what are the unique features of thermal management for lithium-ion cells. There are a few unique challenges that exist in the cooling of lithium-ion cells that I want everyone to be aware of. So the first thing is that oftentimes weight or volume is an important challenge, right? If I have an electric car that has a big battery pack that needs to be cooled, then I don't want to add to the weight of the car because of the thermal management technique, right? So for example, if I have a pack containing a bunch of lithium-ion cells and I decide that I'm going to cool it with liquid water or let's say air, if I'm going to blow air over it, then I need a fan, I perhaps need a filter, and I need several other equipment in order to make this work. Each of those things will have a weight and a volume, right? When I design an electric car, weight and volume are both limited. And the same problem also exists in a bunch of other applications of lithium-ion cells like spacecraft and consumer electronic devices and so on and so forth. The second consideration is that of power. This fan, which will blow air over it, will consume power. Where will that power come from? It will probably come from the cells themselves, right? So what that means is that I now have lesser power available to do the job that I really want to do, which is to move the car, right? So what percentage of my energy stored will be used up simply for cooling the cell is an important parameter that I want to track, and that number should not be more than maybe a few percent at most. If say 25% of this power is being used for just for cooling it, then that's not ideal at all. Okay, so weight and volume, power, and a practical consideration also is that of cost. So I think these are the top 3 practical considerations in designing a thermal management solution. In addition to that, as far as the characteristics of this are concerned, we talk in terms of delta T. I don't want to call it delta T. Temperature reduction per unit power is an important metric for any thermal management technique. In other words, for every 1 watt of power consumed by the pump or whatever other equipment that I am using, how much is the reduction in the peak temperature that I am able to get. This is sort of like what I get divided by what I need to pay to get it, right? So whenever we design or evaluate a thermal management system, this is a parameter that I want to track, and I want to make sure it is as high as possible. Then in addition to that, in the world of lithium ion cells, one very specific consideration is delta T, which is the temperature difference across the cell or the pack. In other words, going back to the previous slide, if I cool down this battery pack by blowing air over it, then the peak temperature in this battery pack will probably occur somewhere here, right? And the minimum temperature will probably occur somewhere here. The difference between the two is the temperature difference across the pack, and that temperature difference needs to be minimized. In other words, not only am I interested in reducing the temperature of the entire battery pack, but in addition, I also would like, if possible, for the battery pack to be as uniform as I can make it. Because if I am cooling down this cell very much and not this cell, then these two cells will age differently. One of them will age faster than the other. The one that is not being cooled very well will age much faster than the other cells. And it turns out, like in life, that the performance of the entire pack is determined by the weakest link in the system, right? And therefore, I would very much like for all these cells to age as uniformly as I possibly can. This in fact applies even for a single cell. So if I have a single cell, and if I'm cooling it by blowing air over it, then clearly the peak temperature in this cell will occur here, and perhaps the lowest temperature will be here. This temperature difference I would like very much to be as low as possible. In the past decade or so, the research field of thermal management of lithium ion cells has really taken off. There are literally hundreds of papers on how to cool down lithium ion cells. What has basically happened is that a bunch of people that have expertise in thermal management in general have identified lithium ion cells as an interesting system and said, okay, I know how to use heat pipes for thermal management systems, let me use heat pipes for cells. Somebody else says, okay, I know how to use evaporative cooling, let me show how to use evaporative cooling for lithium ion cells, and so on and so forth. Okay, this still continues, in my opinion, to be a rich area in which to do work, because I don't think all the problems have been solved yet. We still do not know a lot of things about thermal management of cells, and any creative ideas about the cooling of cells is taken very positively in the research community. So if you guys have any ideas, any thoughts about cooling of cells, go forth and explore. What I will do is that I will list out a number of different techniques that I have seen on the cooling of cells, and in fact let me see if I can, where do I go? No, not this one. So this paper that just got published, some collaborators from China and I wrote a review paper on indirect liquid cooling of lithium-ion cells. It's a good paper. It's a long paper, 31 pages, but I think it does a very good job of summarizing the literature on air cooling, liquid cooling, phase change cooling, heat pipe cooling, etc. And it gives lots of different examples of different types of work that people have done. So if you are interested in thermal management of cells, this is a paper that you might benefit reading from. What I like about it is that it is very comprehensive. Lots of figures and stuff, and lot of in-depth discussion of what others have done. And it has like 200 or so references in the end. 179 references. Okay. So this is the paper, just came out. Yeah. Let me go back here and make a list of different approaches for thermal management of lithium-ion cells. The most common approach is air cooling. Why? Because air cooling is cheap, air is commonly available, all you really need is sort of a fan, right? So there is a lot of papers on air cooling of lithium-ion cells. The other common technique is liquid cooling. In some sense, the literature in thermal management of lithium-ion cells has followed the same path as computer chips. When computer chips started getting hot in the 90s, the first approach was to use air cooling. And then when people figured out that air cooling is not going to be sufficient is when they moved on to liquid cooling and then evaporative cooling and other more advanced techniques. Sort of the same thing is happening in the field of lithium-ion cells as well. Air cooling is the fundamental, easiest, cheapest, but it has its own limits. So then the next one is liquid cooling. Within liquid cooling, the most common liquid coolant used is water. But a key disadvantage of water is that water cannot make direct contact with your cells. You can blow air over your cells, sure, but you cannot blow water over the cells because the water is going to short your cells. So almost always there needs to be a sort of like the cooling has to be indirect. There has to be a thin sheet of something that separates the water and the battery pack that you're trying to cool. Okay? But nevertheless, water has very high heat capacity and reasonable thermal conductivity, and therefore the performance of liquid cooling is certainly better than air cooling. The cost that it comes with is greater weight and greater volume, because with air you can always cool the pack and then reject the air into the surroundings, right, because there's lots of air around. But with water you have to design a closed loop system where the water that you use for cooling the cells comes out of the pack, then that water itself has to be cooled down, so there needs to be a secondary heat exchanger, so that you can then take the same water and circulate it around in a loop. So then you need a pump, you need good piping, you need another heat exchanger, and it just becomes a lot more complicated. And in the context of an electric car, any system that you design needs to be able to run for at least 10 or 15 years. So reliability becomes an important question. Any one of these parts that fails can fail the entire electric vehicle. Okay? In this context, immersion cooling has also been looked at in a lot of detail, and I'll show an example shortly. The basic idea being that with water, since you cannot directly flow over the cell, therefore there is always a thermal resistance between the cell and the water. Whatever you put on top of the cell or the pack offers a thermal resistance, and that reduces the performance of thermal management. And therefore there is motivation in taking some sort of a liquid and being able to flow that liquid directly on the cell or the battery pack. And if you want to do that, the most important property of the liquid is that that liquid should not conduct electricity, because if it is flowing right above or on the cells and all the wiring, etc., then any short will just kill your battery pack. So this needs dielectric liquids. Fortunately, dielectric liquids are not new. Dielectric liquids have been used for the cooling of at least two other systems that I am aware of. One is computer chips. So there are papers out there on taking a computer chip and instead of cooling it with a heat sink or a fan, blowing this dielectric liquid over it directly. The dielectric liquid can touch all the wires and connections and everything without causing a short. There are some very well known dielectric liquids. The one I am most familiar with is called FC72. You can easily go and buy FC72 and get started. It's not very expensive either. Okay. The other area in which dielectric liquids have been used for cooling is transformers. High power transformers actually sit in a bath of oil that is circulated and it is cooled on a continuous basis using immersion cooling. Okay. In addition to air cooling and liquid cooling, some other techniques that I have seen in the literature include heat pipe cooling, and I will show an example of this in a paper from our lab. Heat pipes are also not new. See, none of this is new. All of these techniques have already been used in other cooling problems. All we are doing here is to adapt these for the cooling of a new system, the lithium-ion cell, and modify it to sort of cover the quirks of the lithium-ion cell and so on and so forth. Okay. In addition to heat pipes, I think the last major one is phase change cooling. Within this, there are two categories. One is liquid to solid. Oops, sorry. One is liquid to solid, and the other is liquid to vapor, meaning melting and solidification or condensation and evaporation. The basic idea is that if the process of melting requires energy. So if you have a lithium ion cell and if you put a bunch of wax, solid wax around it, then that wax is capable of absorbing heat from the cell and melting, and in the process it is able to take up a lot of heat from the cell and cool it down. Similarly, if you surround the cell with a film of liquid, then as the cell gets hot, that liquid film will evaporate and as it evaporates it will absorb a bunch of heat from the cell. In both cases we will see some cooling of the cell. This melting has been looked at in a lot of detail. There are again literally hundreds of papers on phase change cooling of lithium ion cells. People have used this PCM, that PCM, this configuration, that configuration. That field is quite rich. I think the area that still has not seen a lot of work is evaporative cooling. In other words, can I have a film of liquid around my cell which absorbs heat from the cell and evaporates, and as a result takes away a bunch of heat from the cell? What are the reasons why this has not been done much? I think one, because most dielectric liquids have very high boiling points. So if I put if I put a layer of FC72 around my cell, then that FC72 will simply not evaporate until the temperature rises to the boiling point of FC72, which is probably very high, right? So on the other hand, water will begin to evaporate at 100 degrees C, right? And if I adjust the pressure of the water, then I can make it evaporate at a lower temperature as well, but water is not dielectric. So in other words, in order for this to work, we probably need a combination that combines the dielectric nature of the liquid with a low melting point. So if you are aware of a low melting point dielectric liquid, then that would be perfect for the kind of evaporative cooling we are talking about. I think my opinion is that within this crowded space, the one niche area that has not seen a great deal of work is probably this. Both experimentally and from a theory or simulations point of view. Perhaps just a measurement of evaporative cooling and its comparison with other cooling techniques will make for a great paper. All right? Any questions or thoughts so far? What, evaporative cooling? Sure, it will. So what do we need? Let's think about it. Say I have a lithium ion cell and I want to do evaporative cooling of the cell. What do I need? How will this happen? Sure, yes. So we might need, I don't want to surround it with a lot of liquid. I'm not trying to do bulk evaporation. I'm only trying to do evaporation on the surface. So what I probably want to do is to have a spray which will spray this with a thin film of liquid, right? And then I need to worry about hydrophobicity and hydrophilicity of the liquid, right? The liquid has to adhere to the surface of the cell and create a thin film. Do you see what I'm saying? and then as the cell heats up, this is going to evaporate, and surrounding all of this I need some mechanism to collect that vapor, because I don't want it to escape into the atmosphere. I don't have an infinite supply of the coolant, right? So all of this needs to be collected and pumped back into the spray. Yes, I agree that all of this will increase the weight and volume of the system, and it will also require some power. How much and how does that compare with the other techniques that we've talked about here? I do not know. That, I think, is precisely the work that needs to be done. Right? A comparison of the performance of evaporative cooling versus other cooling techniques. Did you have a question? Sorry?
Regarding immersion cooling,
Yes.
is still available for the research?
I'm gonna talk about immersion cooling in a lot of detail. Yes. So for the rest of this lecture, what I would like to do is to take up 3 of these topics that I have listed here, in which we have made some contributions, and open those papers and discuss those in detail. So air cooling, heat pipe cooling, and immersion cooling. Yes. Yes. Possibly, I have seen that. Yes. Yeah. So the spray is just sitting there. It's not operating continuously, but whenever a temperature sensor says that, look, I'm getting too hot, it just sprays it and just for a little bit cools it down. Absolutely, that is certainly possible. Just a last ditch safety measure. Sure, absolutely. So our lab has sort of been focused more on the fundamentals of heat transfer in cells, and honestly we've not really done a lot of work in thermal management, but here and there we have contributed in a few different fields, and so I'm going to talk about each one of them. Which one shall we start with? Let's start with immersion cooling, why not? So this was a paper by Swapnil Salvi, who was a master's student here with Dr. Tyagi, and then he came to my lab. Very nice fellow, very easy to work with, and very friendly. So he went to Southwest Research Institute, which is a private research company in San Antonio, Texas. He spent a summer there, and then after he finished his PhD, he went back there full time. Funny thing is, when he was interviewing for a full-time position, I asked him how was your interview. He smiled at me and said, Dr. Jain, it was cool. It was just a reunion. He knew all the people already because he had done a summer internship there, and so it was more or less a formality for him to go there after his full-time position. So what he was interested in and what the company was interested in was how to carry out immersion cooling of a battery pack of lithium ion cells. So as I have said, immersion cooling means that you take the cell and you basically immerse it in a dielectric fluid, and then you pump that fluid in and out, sort of like a heat exchanger, in order to remove heat from the cell or the battery pack. At this time, this was 2022 or 23, is when all of this happened, during the COVID time. And at that time, since then, there's actually been a lot of other papers on immersion cooling as well. But I'm presenting this since I'm most familiar with the details of this work. So let me just show you the setup that he had put together. I'll come to that in a moment. Let me show you this first. So this is a picture of his test rig. It's sort of difficult to see the details here, so let's take a look at the schematic instead. What he has is a pack of 7 cells that are put together. So it's a fairly small battery pack. The typical battery pack of a lithium of a electric car has thousands of cells. So this is a reasonably small battery pack. It's a module, exactly. They are all connected to each other through bus bars, and then he puts it in a test rig with an inlet and an outlet. You can sort of see the test rig here, and through this inlet and outlet he can blow or pump dielectric liquid in and out, thereby cooling the cell. Of course, these cells are also electrically connected to the outside world so that I can charge and discharge the cell at any rate I desire. And the outer setup looks like the following, where these are my cells, this is my test rig, and there are thermocouples and flow control valves and flow meters and an external heat exchanger. This dielectric fluid that comes out gets hot and needs to be cooled down before you pump it back. So there is an external heat exchanger, after which it goes back into the test rig. So this was sort of the measurement that he had done. It's not a straightforward setup. It took him probably the entire summer to set it all up. What he found was very interesting. If he found that by comparing the temperature of the cells with and without immersion cooling, it was clear as expected that the temperature of the cell goes down as a result of immersion cooling. What was more surprising was that it turns out that immersion cooling of the cells caused a reduction in the electrochemical performance of the cells. So he carried out measurements of the cell capacity. So he took this setup of cells being immersion cooled, and he ran this setup through multiple cycles of charge and discharge, perhaps thousands of cycles if I remember correctly. Over his entire experiment ran 28 days. So over 28 days the cells were being charged and discharged and charged and discharged, sort of like that figure that we just saw. Yeah, so this was just discharge, rest, charge, discharge. So the cell is going up and down, up and down, up and down all the time. This is plotted for 1 RPT, 24 hours, right? He had done this for 10 RPTs for about 10 days or some such long period. And he found that as time passes, there is a reduction in the capacity of the cell as expected. However, the reduction in the capacity of immersion cooled cells was slightly larger than baseline cells that were not being immersion cooled. So our hypothesis was that what is basically happening is that the immersion cooling is working too well. In other words, it is cooling the outer surface of the cell so much that there is a temperature gradient within the cell. The core of the cell is much hotter now than the outside of the cell, because of which it is well known that a temperature gradient in the cell causes greater capacity fade in the cell. So while immersion cooling is good for thermal management, we found that we still need to tune it in order to minimize these. It's not a great effect, it's only maybe 1% additional capacity fade, but nevertheless this needs to be understood fundamentally, and one may need to design the thermal management system to minimize this undesirable effect. So the rest of the paper was simply on running a bunch of experiments to try and understand how, to try and understand the mechanisms behind this capacity fade. Some of the electrochemical work that he had done, I myself don't understand fully, but to help with that, he also ran numerical simulations of the immersion cooling process. This is fairly straightforward. Yes.
In the base case,
Yes.
the temperature that I'm expecting, is it at the center?
No.
Going to be higher compared to the reverse cooling, or is it
Yes, yes, absolutely. So, let me draw it here. So, without cooling, I expect the max temperature to be here and the min temperature to be here. They are both quite high. Okay. With cooling, they will both come down. But the min temperature will come down so much that this temperature gradient goes up, and that is not desirable. Some people will argue that this scenario is worse than this scenario. They will say, can you do something so that the core cools down and the surface doesn't cool down? It's okay if the surface doesn't cool down at all. That is better than the surface cooling down too much. Because the temperature gradient within the cell causes non-uniform aging of the cell. And that's not good for the health of the cell. The aging of the cell is temperature dependent. And in this case, the core of the cell will age much faster than the surface of the cell or the outer regions of the cell, and that causes an imbalance in the electrochemical performance of the cell.
so let's say the cell is made of a gel.
Yes,
So in some way, a cell is not a single bed bed cell.
Yes.
We have some multiple subcells in some way.
In some
There
way,
are
yes.
multiple,
Yes,
anodes, there are multiple.
correct,
nodes. So in that way, it consists of various subcells.
correct.
So now I'm saying I have two scenarios. In one, I have the one cell, which
Yes.
is a subcell, which is at the center is getting immediate faster.
Yes.
Then also it will be better than the other case where they are not able to.
Well,
understand that
so I don't know the electrochemical reasons behind it, but what they say is that the the deterioration of the cell should be as spatially uniform as possible. I don't want one part of the cell deteriorating much faster than the other. I don't know. I don't know the details myself.
the addition will be done. Like
Right.
how much total addition of the capacity there is.
Yes.
But even if the whole one is totally damaged in some way.
Yes.
By like let's say there are 10 subcells.
Yes.
The last first the core and the center is totally damaged.
Yes.
But if 9 are performing well,
Yeah.
I expect only 10% reduction in the
No, but
capacity.
the argument that I've heard is that the weakest link in the system determines the performance of the system. Sort of.
Will the part of it
Is worse. Yes.
deteriorate, then the other part will not be worse. Because it's completely thin and
Somehow, yeah. I don't know. I don't know.
Last question.
Yes.
So will it be different for a prismatic and the selective system?
No, this principle applies in general.
In prismatic cell,
In prismatic cells also, the temperature gradient within the cell is important and should be minimized. However, if I think of a prismatic cell
so there
versus a circular cell, cylindrical cell, because of the poor thermal conductivity, the temperature gradient is expected to be larger for the cylindrical cell than for a thin prismatic cell. Right? A thin prismatic cell, the thermal resistance within the cell is very small. And therefore, this non-uniform cooling problem is particularly relevant for cylindrical cells. And from that point of view, one rule of thumb is that your cylindrical cell should not be very large. The radius of the cell should be as small as possible. Much better to have a larger number of smaller cells than to have one big hunk of a cell. Yes.
right with the changing of orientation.
We have not. No, this was all done in one.
There will be some effect if we change the orientation.
You mean gravity?
Yeah.
Yes. Sure, perhaps. But keep in mind that this is all forced convection cooling. This is not free convection. So why will gravity play a role?
And one more thing, why we
Yeah, but as you know, forced convection is much more effective than natural convection. So if I stop blowing, if I stop pumping this coolant, then there will still be some circulation because of buoyancy within this, and there will still be some cooling, but that cooling will be very, very little compared to forced convection. If I was to see, um, if I was to have in this test rig my cells, if these are surrounded with a liquid and I'm not circulating the liquid, then not a lot of heat will be removed, right? What I can certainly do is that I can control the flow rate through my pump to blow only or to pump only as much uh, coolant as I really need to cool it down. That I can certainly do. But I probably don't want to make it zero. If I make it completely zero, then I will not have good cooling at all. Okay? Yes. Yes, it is the maximum temperature in the pack minus the minimum temperature in the pack. That's the delta T. Yes, so this is the top ones are max temperatures and the bottom ones are min temperatures. And the three cases that I have drawn, one is baseline, second is immersion cooling, and the third is what I will call as ideal immersion cooling. Okay? We have learned in previous lectures that the thermal conductivity of a lithium ion cell is very poor, 0.2 watt per meter Kelvin or so, right? And therefore, this problem of temperature gradient inside the cell is inevitable. There will always be a temperature difference between the core of the cell and the outside surface of the cell. The only way to prevent it, the only way to prevent this temperature difference is to directly cool the core of the cell. Anything that I do to cool the cell on the outer surface will cool the outer surface effectively and will not cool the core of the cell effectively. That gives us a motivation to investigate how we can possibly cool the core of the cell directly. The simplest approach for that is to make an annular cell. Imagine if I have a cell with a tiny little hole in it through which I can blow air. That way, there is some air blowing on the top that cools the outside, there is some air blowing through the annular hole that cools the inside, and I am getting the best of both the worlds, right? Unfortunately, before people realize that, the manufacturing infrastructure for these cells had already been figured out to build a solid cell. And so now it is very, very difficult to go to a manufacturer and say, can you please redesign your manufacturing in order to have a hole in the middle of the cell? It is too disruptive for manufacturing. Keep in mind that these cells need to be hermetically sealed because the electrolyte cannot evaporate. And so you have to redesign the whole cell in order to be able to provide a hole in the center of the cell. Nevertheless, we have tried this out in our lab just to see what the impact of this is going to be. So, since we did not have a cell with a hole, we made a hole in the cell and inserted a heat pipe to see what happens to the thermal performance of the cell. Okay, so that is the next paper that I want to talk about, and that is Dean Anthony, who was a master's student in our lab. He was a physics teacher, a high school physics teacher, who for whatever reason decided that I want to go back to school and get a master's degree. And so he came to our department, and a very interesting, very nice guy. I met him 6 or 7 months ago. He's doing very well after finishing his master's. Huh? Now he works for a defense company called Northrop Grumman. It's an aerospace defense company, and he cannot tell me exactly what he does. Huh? No, he did not go back to. He wanted to get out of it, essentially, and he thought of this getting a master's degree as his ticket out of high school. Yeah, he does something to do with satellites and the trajectory of satellites and all that stuff. Nothing to do with batteries, by the way. A lot of my students, having contributed to a lot of our work on batteries, are no longer actually doing batteries, right? And I'm quite sure that I'm also going to go and do other things in my life. I'm not going to do batteries all the time. My focus is already shifted to other more fundamental questions, and I think that is the fun of academia. Through students like you guys, we are able to shift directions and identify new interesting problems to work on, and have an interesting life, not monotonous. And the other two authors on this paper, Derek Wong and David Betts, were our collaborators in the electrical engineering department, who knew a lot about the electrical aspects of batteries. So here is a cell that we purchase from wherever. We basically drilled a hole in the center of the cap of the cell to be able to insert a thin heat pipe into the cell. One challenge was that this cell, I think, is an 18, it's a 26650 cell, so its diameter is about 26 millimeters, maybe about this much. I want to drill a hole in the center and insert a heat pipe. This heat pipe needs to be very small, right? I don't want the heat pipe to be occupying 50% of the volume of the cell itself, right? Then what is the point? Then the capacity of the cell will go down so much that I will not have an effective cell. So we needed to find very thin heat pipes, and that is where a friend of mine from China helped. He runs a heat pipe company in China, and he donated to us a bunch of really thin, I think these were 2 mm or 3 mm heat pipes that he makes for some client, and he was just happy to give it to me like candy. And so we drilled a hole, we inserted a heat pipe along with a thermocouple wire on the heat pipe body, because we wanted to measure the core temperature as well. And then we put some sort of an epoxy sealant around it and connected it for electrical connections and all that stuff. And our success rate for doing all this was about 30%. So we tried this on 3 cells, 2 of them immediately die, because the process of drilling a hole in the cell, inserting a heat pipe, etc., will cause some sort of a short somewhere, and the cell does not work anymore. One of the cells survived. All the measurements were done in a hurry on those cells. I think Dean did not go back home that night, and because the cell was also slowly dying, no matter how well you seal it here, we don't have manufacturing level precision for sealing, and therefore the electrolyte will begin to evaporate and the cell will die within a few days. So we were in a hurry and we wanted to take all the measurements we wanted before that happened. So I remember, before we committed to drilling a hole, we already knew from some past measurements that this is not going to stay with us for a long time. So we already had a plan, all the equipment was in place, we knew exactly what measurements were needed in order to make a nice paper, and then it was execution time. As soon as it was made, we tested it out in David's lab, and when he said the cell is okay, we just went and did a bunch of measurements before the cell went away. So remember, what was the motivation of this? The motivation of this was to cool down the core of the cell, right? The outside part of the cell is easy to cool. I'm not too worried about that. I'm worried about the core of the cell that needs cooling. And it turns out, as expected, that we got some very nice results. First of all, we carried out electrochemical characterization of the cell. So we carried out a voltage versus time measurement, and we carried out an EIS, electrochemical impedance spectroscopy. It's basically a measurement of the health of the cell, the key characteristics of the cell, sort of like its blood pressure, its temperature, etc. and we show that uh, red is the control cell, blue is the heat pipe cell, the cell with the heat pipe, and the two of them are fairly similar to each other. There were some differences in the EIS which David and his student were able to explain. They had a better idea of what EIS means and so on. By the way, we have always benefited from good collaborations. We don't know everything. There are others who have a particular expertise in some other field, and I've always found that it's very helpful to shake hands and work with somebody who has a complementary expertise. So you all should not hesitate to try and find those collaborations. If there is something that you don't know very well, is there somebody else in your institute or even outside who can help you with that? Trust me, people are always looking for such collaborations themselves. And creating teams like this is really what leads to good, solid work. Then we carried out temperature measurements. And so this is measurement of the core of temperature at the core of the cell. Red is without heat pipe. Yellow is with the heat pipe, but the heat pipe is inactive. In other words, let me just draw it here or here. Here is my cell. Here is the heat pipe inside the cell. The heat is going to go up through the cell. But in order to actually remove the heat, I also need to blow air over the tip of the cell. If I don't blow air over the tip of the cell, then having a heat pipe is meaningless. And that is actually what the yellow curve was. So even without any air blowing over the cell, I still got some decent benefit in the core temperature. And when I started blowing air over it, there was even more benefit in the cooling of the cell. And then we looked at the effect of the speed of the fan, and as expected, the more air I blow over it, the more cooling I get. As you can see, this is sort of applied work. We are sort of trying to see how things will happen in real life, right? There are no equations here. There's no basic science here. Yes. This was all happening at 20 amps discharge. And I think this was a cell, the cell capacity, let's see. I think it was about 2 amps or something like that. Two amp hour cell, 2.8 amp hour cell. So the C rate was about 10C, 7C or something like that. 7C is an extremely high discharge rate. Yes. We are looking at 20 amps of current. How many amps of current will kill you? If you're going to do research in this field, please, before that, find the answer to this question. How many amps of current will kill you? I think a few amps of current is a lot of current, right? Typically, in electrical measurements in the lab, usual measurements, we talk about maybe 1 amp at most. This is 20 amps of current. It's a lot of current. Please be careful. Yes. It was probably a secret sauce that he does not tell anyone. Any other questions on this? So then we were also interested in, as we said, understanding the temperature difference between the outside and the inside. Why don't we focus on part B specifically? So part B plots the temperature difference. The red is the baseline, the insulated heat pipe. You can see that there is a significant temperature difference between the inside and the outside, 12 degrees C. The usual recommendation is not to exceed 5. But on the other hand, if you look at the other curve, in the presence of the heat pipe, the temperature difference between the outside and the inside stays pretty close to 0. And in fact, somewhere towards the end, it even becomes negative. Which is very unintuitive. It can only be explained on the basis of the presence of the heat pipe. The heat pipe is doing such an excellent job that it has turned the problem on its head. We used to be worried about the core being hotter than the inside of the cell. So this sort of provided us a proof of concept that inserting a heat pipe into a cell can be extremely beneficial in removing heat from the and how the core of the cell is not being cooled very well. Here is a technique to do that. The only problem here is that our experimental setup was very crude. Drilling a hole in a cell and inserting a heat pipe is not remember we said about those electrode layers being rolled around a mandrel in order to create the jelly roll. Exactly. The mandrel in usual manufacturing itself, and never let it out. Just keep it there. Hmm. It can possibly short, yeah. So those are things that one will have to and it might perhaps provide the kind of insulation you're looking for. Also keep in mind that this heat pipe will have to come through the cap of the cell. So the cap and all the other safety features we talked about under the cap will all need to be redesigned. And come out, and then you would have to provide some sort of sealing around the heat pipe in order to make this work. And of course, for all of this to work, cost is also an important consideration. If I have a lithium ion heat pipes,
What is the price of that heat pipe?
for us it was priceless because there was no manufacturer in the world who was able to manufacture at that time, this is 2016 or so, a 2 millimeter diameter heat pipe. My friend said, yes, I of a more regular size costs of the order of $50 or so. If I purchase a few of them, if I am a manufacturer who's going to purchase 1 million of them, then I will get bulk pricing and it will be lower.
50%.
Yes.
Then the price of cell in India is around 500 or 700.
Yes.
The
Heat pipe is more expensive than the cell. Yes, absolutely. Yes. You know, that is not necessarily a reason to stop working on this, right? We don't worry about cost as much because when things begin to happen in bulk, the cost does come down. The cost of batteries also 15 years ago was much higher, right? And the expectation is that as the world adopts a technology, the price does come down.
generally the manufacturer doesn't want to imply at current time that it can increase the who will purchase the cell.
Yes, absolutely, absolutely. Any other questions? So, I think that is all that we had said in this paper. And you know, I think this is also a good one to look at. This is temperature rise versus time for different currents. So, sorry? For the same cell with and without heat pipe. So solid line is without heat pipe, dashed line is with heat pipe, and the colors represent the 5 different currents at which we did it. So at a very low current, there is a significant reduction in temperature, and that reduction becomes more and more significant as the current goes up. So for example, at 20 amps current, which is a lot of current, the peak temperature rise was 50 degrees C without the heat pipe, and only about 37 degrees C with the heat pipe. That's a 13 degrees C temperature improvement, which is very nice. Sorry, what?
One series at the end of this, it is approximately 5 minutes.
Correct, yes. Yeah, which is not much, right? One advantage of heat pipe cooling is that it is passive in nature. The heat pipe is just sitting there. You don't have to pump the cooling fluid, the working fluid inside it and so on. All you need to do is to blow air outside at the other tip of the heat pipe, which is not very expensive, right? So for that reason, anyway, for that reason, heat pipe cooling is very attractive. Most of the papers in this field have inserted heat pipes between cells. So if I have a large battery pack such as this, I would place heat pipe here, here, here and here around the cells. But the problem is that the rate limiting step lies inside the cell. The thermal conductivity of the cell is so poor that the most difficult step in this journey is thermal conduction within the cell. And that is the motivation for inserting a heat pipe into the cell in order to remove its heat at the very core of the cell. Okay? Any questions? Yes. हाँ, dielectric fluids की thermal conductivity usually कम होती है. See, electrical conduction and thermal conduction usually go hand in hand. A material that does not conduct electricity, like a dielectric fluid, usually also does not conduct heat very well. What? Yes, because that will conduct electricity. There's a trade-off here, right? You don't want to short your cell. So clearly you cannot use a conducting liquid like water. If you use water, the cell has to be physically separated from the water. There has to be a barrier over which the water flows. It cannot come in direct contact with the cell, right? If you aspire to have the liquid touch the cell, then the non-negotiable requirement is that it should be electrically non-conducting. Uske baad, if it does not conduct heat very well, bad luck, what can you do? In the world of material science, I think this is an open question of designing materials with dissimilar thermal and electrical properties. Can you design a material that does not conduct electricity very well, but conducts heat very well, or vice versa? Those materials can be of a lot of use, not only in cells, but in a wide variety of other engineering systems. Okay? Sorry? Good question. The bus bar and the heat pipe cannot touch each other, because then the electricity will enter the heat pipe and all sorts of bad things will happen. So you have a point. In order to make this all work, you probably also need a hole in the bus bar itself through which the heat pipe can come out, and perhaps some sort of a insulating O-ring in order to prevent contact between the heat pipe and the bus bar, right? Yes, absolutely, these are all valid practical questions that will need to be addressed if this has to happen in reality.